Hello everyone, welcome back to Spectrum classes. I have already made one video on calculating number of components and this video is in continuation to that video, so please go and check that video, and here we are solving some more examples. Now we are going to discuss the example of decomposition of water liquid in the form of hydrogen gas and oxygen gas. First we are going to discuss the number of phases for the given system. So this is of two-phase system. How we are going to say this? So here we are having one phase as liquid phase and the other phase is as gaseous mixture. So it is a two-phase system. Now coming to the number of components. So if this decomposition is carried out in a closed vessel, it means the hydrogen gas produced is equal to the oxygen gas produced. So the partial pressure of hydrogen gas is equal to the partial pressure of oxygen produced, right? So if we are calculating the number of components by the formula C is equal to N minus E, where N is the number of species, E is the equations relating to their concentration terms. Then number of species we can count from this equation or from here also, right? So this is 1, 2 and 3, or you can measure this 1, 2 and 3. So 3 number of species and 2 equations are there. One equation, second equation. So on putting the values, we come to know that this is one component system, or we can say the each phase of this system can be described by the component H2O only. So in case of gaseous mixtures formed by the decomposition of any species in a closed vessel, that will be considered as one component system. For example, we are having here. If some of the exceptions are there, then guys, I do not have much idea about. Now coming to the next example. Dissociation of calcium carbonate solid into calcium oxide solid plus carbon dioxide gas. Number of species are 3. Now coming to the number of phases. So here 2 solids and 1 gas. So these 2 solids are different. So these comprise to 2 different phases here in this system. It is a 3-phase system, 2 solids and 1 gas phase. Now coming to the number of components, how many components are required to describe all 3 phases of this system. So first I will solve this example with 3 different types. First, with the equilibrium pressure constant. So if we write the equilibrium pressure constant for this equation, then it will be equal to the partial pressure of the product divided by partial product of the. So here we are having partial pressure of calcium oxide into partial pressure of carbon dioxide divided by partial pressure of calcium carbonate. Since calcium carbonate and calcium oxide both are in solid state, so their partial pressures or their activities will be considered as 1. If these two are 1, then this equation will be simplified as partial pressure equilibrium constant will be equal to the partial pressure of carbon dioxide. So to explain or to describe the gaseous phase, we come to know the concentration or the partial pressure of carbon dioxide. Coming to the solid phase. So out of these two solid phase, at least one solid phase must be known to us. Then one solid phase and one gaseous phase, if known to us, then we can fix the third one. So this is one way. If we are going with the formula C is equal to N minus E, then how we are going to measure the number of species? 3 species are there from this equation. How many equations are there? So one equation is. So now putting these values in the formula, C is equal to N minus E is equal to 2. From this equation, we come to know it's a 2 component system, and if we are comparing this with this equation, then it is again a 2 component system. I will give you some more examples which are of same type. Here KClO3 dissociates as KCl solid plus oxygen gas. Copper sulfate pentahydrate dissociates as copper sulfate trihydrated solid and water vapors. So here in this case crystalline water is released. So dissociation of this calcium carbonate is a 2 component system. This is given in several textbooks I have come across. So if calcium carbonate and calcium oxide, two solid phases are known to us, then we can fix the third one. How we can fix that? So if calcium carbonate is known to us, means it is pure calcium carbonate, no calcium oxide is there. Coming to the calcium oxide, which is known to us. So it means no calcium carbonate is there, only pure phase calcium oxide there, which is known to us. Now on subtracting these two, we get carbon dioxide as a gas. So this is how it is given in the textbook. Now suppose rather knowing the calcium oxide, if we know calcium carbonate along with carbon dioxide, then this system can be written like, right, calcium carbonate means pure calcium carbonate, no carbon dioxide is there. Calcium oxide we need to determine now. So how we are going to determine that? Calcium carbonate minus carbon dioxide. Then we can fix this calcium oxide. Now coming to the carbon dioxide, which is known to us, it means it is, we know pure carbon dioxide, no calcium carbonate is there. Now I will give you this example in this manner. If we know calcium oxide and carbon dioxide, then how you are going to fix this calcium carbonate. So guys, you just write down by yourself. So I'll give you the clue. If we know these two, then we add the concentration of these two, we will get the calcium carbonate. So I have solved this here, so you can go through with this, right? Now coming to the example of association of or combining of hydrogen gas with iodine gas to form 2Hi as a solid, right? So how we are going to measure this? So here we are having three species. And how many equilibriums are there? Only one equilibrium is there. On putting these two values in the formula, C is equal to N minus C, we come to know that it is a two component. Out of these three, we must know two components at least to define the two phases of this system. One is gas phase and the second one is solid. So it is a two phase and two component system. I have also solved this with the help of this equilibrium constant. So suppose if we write for this given equilibrium, the equilibrium constant in partial pressure terms, then we have this partial pressure of hydrogen iodide divided by partial pressure of hydrogen gas into partial pressure of iodine gas. If hydrogen iodide is in the solid form, then its partial pressure will be considered as 1, as I discussed in the previous slide. And if the condition is given that partial pressure of hydrogen is not equal to the partial pressure of iodine, then you just put all the values here. So this is 1, this is known to us. Then out of these two, at least one value must be known to us. So on putting that value, we can evaluate the third one from here. So one is known to us, we will be able to evaluate the third one, and on combining, and if we combine these two together, we can fix the third one. So it is a two component system. Here we are having the condition H2 is not equal to I2. So this is how this system can be evaluated by the two component system. This example I again solve with the help of this condition. If H2 is equal to I2. So here we are having two equilibrium. I also explain this example with the condition of hydrogen is equal to iodine. Right? So from here, this is the equilibrium constant and we are just putting the value of Hi, which is 1, and these two are equal. So rather writing partial pressure of hydrogen and partial pressure of iodine, we can put partial pressure raised to the power 2 of hydrogen or iodine, right? And if we know this equilibrium constant, then we can evaluate. So from equilibrium constant, we can evaluate the partial pressure of hydrogen or partial pressure of iodine. And since we come to know the partial pressure of hydrogen or iodine, we can evaluate the second one. And since these two are in equal amount, then on combining these two, we will get the concentration of Hi. So here, if we apply this condition again, then number of equations will change to 2. Here 1, no other concentration condition is there, but here in this case we are having the second concentration. So this is one component system and this is two component. Now coming to the next example. This example is asked in several competitive exams. Explain why KCl, NaCl, H2O system should be regarded as three component system, whereas KCl, NaBr, H2O system should be regarded as a four component. So I am going to solve this. Here, how many species are there? We are having three species. Number of equations or equilibriums existing in these species. So no equilibrium is existing in these three species. On putting the values of N and E, we can evaluate the number of components. So it is a three component system. This is simple. Now coming to the KCl, NaBr and H2O system. Here, in this case, and equilibrium exists in these, yes, there is one equilibrium, that is double displacement equation or equilibrium is existing in these three species. Now number of species, three species, and KCl we considered here, NaBr we considered here, H2O we considered here, three species. But because of this double displacement, we are also having KBr and NaCl, where double displacement is taken. So it's a 5-species system and number of equilibriums existing between them, 1. So it is a 4-component system. Now coming to the next example, determine the number of components. So this is given here. In continuation with the previous example, here I have chosen this because here it is given solid and solid, ions, 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 liquid and gas, right? So it means solid as well as ions are existing, means there is an equilibrium condition between the solid and ions. How we are going to solve this? So just to solve this in steps. So in the first step, establish the equilibrium relations in the given. So you are familiar with this NaCl solid. We have already discussed in my previous video. So it is dissociated as Na plus Cl minus. One equilibrium. Second is for KBr, K plus Br minus, and double displacement reaction, which I have given in my previous example. And since here plus minus charges are involved, it means electrical neutrality is one of the conditions. So here in total 4 equilibrium or 4 equations are exist. Now coming to the number of species. So in this case 9 species are there, right? Water is considered with as a one species and rest of the species are considered each 1, 2, 3, 4, 5, 6, 7, 8 and 9, right? So 9 species are there, 4 equations are there, and now putting the values of number of species and equations in this formula, we are getting it's a 5-component system. Difference in opinion, somewhere it is given 5, somewhere it is given 4. So in my opinion, it's a 5-component system. Now coming to the next example of same kind is given as NH4Cl solid, NH4 plus aqueous, and these are the actually number of species which are given over here. So the first step which we have to follow is to establish the equilibrium between the ions dissociated and undissociated solid species, right? So here the first equilibrium which I have written over here is NH4Cl solid is in equilibrium with NH4 plus aqueous plus Cl minus aqueous. The second equilibrium which I have written is H2O liquid on combination it forms H3O plus aqueous plus OH minus. Here the NH4 plus which is produced in the first equilibrium that reacts with the OH minus which is produced in the second equilibrium and form NH4OH, which is given as one of the species here. Now the next equilibrium, this NH4OH is in equilibrium. It dissociates like NH3 gas plus H2O gas. Since plus and minus charges are involved in these equilibriums, therefore, so electrical neutrality equation is also there. So this many equilibriums are established in the given species here. One more important thing which I bring to your notice here is that Some of you may also write an equation like H2O liquid on reaction with Cl minus will forms HCl and OH minus. But guys, what I have perceived by following so many texts and literature and several examples I have gone through, so the species which are given in your question, only follow those species. Don't go by yourself. So here, if HCl is not given, so don't go for the HC formation. In different books, different type of methods have been followed to solve the number of components. So whichever you feel good, you go with that. But I'm just here sharing my experience with you. Now coming to the number of species. So number of species are 8. 1, 2, 3, 4, 5, 6, 7 and 8. H2O gas and H2O liquid is considered as 1. Number of equilibriums 4 plus 1 is the electrical neutrality, so 5. Now putting these values in the formula C is equal to N minus E, then we are having 8 minus 5 which is equal to 3. It means it is a 3 component. So I have here highlighted the 3 important species which are required to describe the whole system in solid as well as in liquid and gas phase. So this is a 3 phase and 3 component system, right? So this is the answer of this question. Now coming to the next question of this type. This question is given as determine the number of components for this system assuming hydrolysis to takes place. Here hydrolysis we have to consider, right? So first what we need to do, we need to establish the equilibrium between the given solid and aqueous ions. So here I have established the following equation or equilibriums in the given species. These are to the best of my knowledge, right? So here this is ammonium acetate solid dissociates as acetate ion aqueous ammonium ion aqueous. This acetate ion on hydrolysis or on reaction with water, it forms acetate, which is one of the species given here, OH minus, right? So OH minus is again given. The next equation, this NH4 plus, which is formed in the first equilibrium, that on reaction with water forms NH3 gas plus H3O plus aqueous, which is also the species given here, NH3 gas. H3O plus is also one of the species. Here OH minus and H3O plus is formed. These two on reaction will form H2. And one is the electrical neutrality. So here in this way, 5 number of equations are exist. Number of species 8. 1, 2, 3, 4, 5, 6, 7 and 8. Number of equations are 4 equilibrium plus 1 5, and in this manner number of components will be is equal to number of species minus number of equations is equal to 8 minus 5 is equal to 3. So it is a 3 component system in this manner. But from where I have taken this question, in that this equilibrium is not considered because these are the products and these products on combination they form H2O liquid or they get neutralized. And for this equilibrium, it's a constant Kw is equal to 1 into 10 raised to the power minus 14 value. But if this is the case, then in the previous question, we have also taken such type of equilibrium. So I'm not sure for this whether we have to take this or this is up to you. Just because of the length of the video, I have collected some more examples here. So you can do these questions in your notebook. And here I am going to describe these questions briefly. So here is the first question in which it is given NaCl as solid, KCl as solid is Na plus aqueous, K plus aqueous, Cl minus aqueous, H2O liquid and H2O gas. So first of all you have to establish the equations or equilibrium conditions. So NaCl solid is in equilibrium with Na plus and Cl minus aqueous. The second equilibrium is KCl solid is in equilibrium with K plus aqueous and Cl minus aqueous. Since it is not given that there is an equilibrium in H2O liquid and H2O gas, so I'm not going to consider that. Two equilibriums are there, and the third one is electrical neutrality. Number of species are 6 here in this question. So 6 minus 3 will be 3. It's a 3 components. Now coming to the number of phases. So solid, liquid and gas. So 3 phases are there. Now coming to the second question. So here we are having calcium chloride hexahydrated as solid and calcium 2 plus aqueous, Cl minus aqueous, H2O liquid and H2O gas. So if we consider the number of phases, so 3 phases are there, solid, liquid and if we establish the equilibrium here, so calcium chloride hexahydrated dissociates as calcium 2 plus, Cl minus and H2O crystalline water. So one equilibrium is there, second is electrical neutrality. So two equations are there and number of species are 4. So 4 minus 2 is equal to 2. It's a 2 component system. Now coming to the third question. So here we are having iron as solid. On reaction with water, it forms iron oxide as solid plus hydrogen gas. So one equilibrium is there and number of species are 4. So it's a 3 component system. Now coming to the number of phases, which is important here because here we are having solid gas, solid gas. So two gases are there. So gaseous mixture is considered as one phase. Now what about the solids? So here this is you can consider as rusting of iron. So it's a iron piece and it's rust powder. So two are mechanically separable. So these two solid are considered as two phases and one gas phase. So three phases are there. Now coming to the question number 4. So it's an esterification reaction. So acetic acid on reaction with ethyl alcohol, it gives ethyl acetate plus water. Here one condition is there that ethyl acetate is equal to the water produced. So two equilibrium equations are there, no electrical neutrality is there, number of species are 4, so 4 minus 2 is equal to 2. The two component system. Now coming to the question number 5. This question I have taken from the research paper, right? So AlCl3 is dissolved in water, noting that hydrolysis and precipitation of AlOH whole thrice, giving various ions Al3 plus H plus AlCl3 AlOH whole thrice, OH minus, Cl minus, H2O, HCl. So if we count these species, so number of species are 8 in this given system. Now coming to the establishing of equilibrium equations for this given system. AlCl3 on hydrolysis, it forms AlOH whole thrice plus 3HCl. AlCl3 is in equilibrium with Al3 plus 3Cl. And since here in this question H plus and OH minus is also given, so I have written this equilibrium. H2O is in equilibrium with H plus and OH. 3 equilibriums are there and one is electrical neutrality. So 4 equations including electrical neutrality. Number of species are 8. So 8 minus 4 is equal to 4. It's the 4 components. So I hope guys this video is helpful to you because so many examples I have chosen here are asked in several competitive exams. And this video also helps you to understand how to calculate the number of components for a given system, how to consider the equilibriums. So guys, if you find this helpful, please like, share and subscribe, and thank you for watching.